Welcome to this session. This session, we are going to discuss the Simpson's 3/8 rule for integration. So, derivation. So recall that the general Newton forward interpolation formula for integration of a function f of x in the interval a, b is, so integral a to b f of x dx is nh into f naught plus n over 2 forward of f naught plus n into 2n minus 3 over 12 second forward of f naught plus n into n minus 2 squared divided by 24. If you don't know how this formula is coming in, please watch the previous videos. So this is by definition. This is what we call star. Now, let the function or curve y equals to f of x be as drawn below. So we have this. This x so let this be the function for the curve y equals to f of x, an arbitrary curve. So the interest is to integrate from a to say, let b be this point here. So integrating, you have to remember that integrating a to b of f of x dx is the same as area under curve y equals to f of x, line x equals to a, and x equals to b. It's like finding the area under this graph. So we divide this region so similar pattern. So this is what we call the x naught. So this x1, x2, x3, x4, x5, x6, xn, xn minus 1, xn minus 2, xn minus 3. So to find the integral a to b of f of x dx is simply finding the area in this region. So what I'm shading It's like we're interested in defining the shaded area. So we say setting n to be 3 in that formula star. N equals to 3 in star above, and taking the curve through the points x0, f0, x1, f1, x2, f2, and x3, f3 as a polynomial of degree 3. Then fourth, fifth, etc. differences approaches 0 or are neglected. So we have from star I1, the integral from x0 to x3. So remember, the difference now between this one and what you have done previously for Simpson third rule is that we are now picking 3 strips at a time. Remember, for Simpson third rule, we are picking 2 at a time. For this case, we are now picking 3 at a time. So we are picking this, we are picking this, and we are picking this one here. So these 3 at a time. So this is the point x0, f0, x1, f1. This is x2, f2, x3, f3. So this height is what is f0, this is f1, this is f2, and then this is f3. So we'll have integral f of x dx equals to, now n is 3, so n times h is 3h into f0. N you put 3, so we'll have 3/2 forward f0 plus n. Remember, we have n into 2n minus 3/12. So 3 into 3 times 2 is 6 minus 3/12. 6 minus 3 is 3 times 3 is 9. So 9/12 is the same as 3/4. So 3 into 9, 3. And then, so that's what we have from, so 3/4 second. And then n into n minus 2 squared over 24. So n is 3. So 3 into 3 minus 1. 3 minus 2 is 1, squared is 1, so over 24. So this one is 8. We have 1/8 third forward. So we'll have, now just remember, forward of f0 is given by f1 minus f0. Second forward of f0 is given by f2 minus 2 f1 plus f0. And third forward of f0 be given by f3 minus 3 f2 plus 3 F1 minus F0. You can always confirm this. So let's now simplify this value for I1. So we'll have I1 equals to 3H into F0 plus 3/2 into F1 minus F0 plus 3/4 into, so where there is second forward of F0, we substitute by its equivalent value, F2 minus 2 F1 plus F0, F2 minus 2 F1 plus F0 plus 1/8 F3 minus 3F2 plus 3F1 minus F0. So let's simplify this. So I'll have I1 equals to, we have 3H. Now I have F0 minus 3/2 F0. Here I have plus 3/4 F0 minus 1/8 F0 plus 3/2 F1 minus 6/4 F1 plus 3/8 F1, and then plus 3/4 F2 minus 3/8 F2, and then plus 1/8 F3. So I1, I've just collected like terms, is 3H into, so 1 minus 3/2 plus 3/4 minus 1/8. That gives me 1/8 F0 or F1 is 3/2 minus 6/4 plus 3/8. That gives me 3/8 F1, and then F2 3/4 minus 3/8. I get 3/8 F2 plus 1/8 F3. So what we do now, we factor out 1/8 because it's on each term here. So we have I1 equals to 3/8 H into F0 plus 3F1 plus 3F2 plus F3. Similarly, now remember, once we have taken the first three, if you go back to this table, this diagram, once you have taken this first three, so this will be the next one, this, and this one here. So the starting one will be F3, this next one will be F4, and then this one will be F5, and then this one is F6. So this region is defined by from F3 to F6. So similarly, we can define I2 will be the integral from x3 to x6 of f of x dx, and that will give you 3h over 8 into f3 plus 3f4 plus 3f5 plus f6. You can also define I3 will be now the integral now from x6 to x9 f of x dx, which will be 3h over 8 into f6 and then plus 3 f7 plus 3 f8 plus f9. We can also define I4 to be now the integral from x9 to x12 of f of x dx, which will be 3h over 8 into f9 plus 3f10 plus 3f11 plus f12. This continues up to the I end of the last integration, because you see these subscripts are always divisible by 3. So we'll have 3n minus 3 up to x sub 3n of f of x dx. This gives you 3h over 8 into f 3n minus 3 plus 3f 3n minus 2 plus 3f 3n minus 1, and then plus f of 3n. So summing up all the integrals, I is given by I1 plus I2 plus I3 plus I4 plus up to In. This will give us I1 was 3h over h into f0 plus 3f1 plus 3f2 plus f3 plus 3h over h into f3 plus 3f4 plus 3f5 plus f6. Next was 3h over h into f6 plus 3f7 plus 3f8 plus f9 plus 3h over 8 into f9 plus 3f10 plus 3f11 plus f12 plus other terms, 3h over 8 into f of 3n minus 3 plus 3 f of 3n minus 2 plus 3 f of 3n minus 1 plus f of 3n. Now, since each term has 3h over 8, then you say I equals to 3h over 8 into, so we have f0 plus 3f1 plus 3f2 plus f3 plus f3 plus 3f4 plus 3f5 plus f6 plus f6 plus 3f7 plus 3f8 plus f9 plus f9 plus 3f10 plus 3f11 plus f12 all the way plus f3n minus 3 plus 3f3n minus 2 plus 3f3n minus 1 plus f3n. Now, you can also see a pattern that this 9 and 9, so we also expect to have an f3n minus 3 here. So that would give us 3h over h into these last ones are never repeated. So we'll have f naught plus f3n plus, now this we have 3 into f1 plus f2 plus f4 plus f5 plus f7 plus f8 up to plus f3n minus 2 up to plus f3n minus 1, and then those with 2 as the coefficient are those which have the subscripts divisible by 3. So we have f sub 3, f sub 6, f sub 9, f sub 12, up to f sub 3n minus 3. And this is the Simpson's 3/8 rule. So this is a Simpson's 3/8 rule. Say this is the Simpson's 3/8 rule for numerical integration, which only applies when the interval AB is divided into subintervals which are divisible by 3. So that's what we have. Just an NB 1 Simpson's third rule is more accurate compared to Simpson's 3/8 rule. We'll see in the examples. And then number 2, Simpson's rules are more accurate than trapezoidal rule. We'll see specific examples to illustrate this one. So that is all about derivations of the 3 rules of integration. Next session, we'll be doing examples to illustrate how they apply. Thank you.